In this lecture, we are going to take a look at some aspects of time-dependent perturbation theory. In particular, what happens to a system when it's exposed to a sinusoidal perturbation. But before we get into that, let me quickly recapitulate whatever we had discussed in the last lecture. As you must remember, what we are trying to do is get a perturbative solution for the Schrodinger equation, IH cross del psi del t equals H psi, and of course H here has a piece which is time independent and exactly solved, H0, and another piece which is a time dependent perturbation which is small in some sense. And when I say H0 is exactly solved, I mean that I know its spectrum completely. All its eigenvalues and eigenvectors are known, and there is a complete set of orthonormal eigenvectors, the phi's. And of course, as I said, u of t is in some sense small compared to H0. So what we did was expanded the time dependent state psi of t in the eigenbasis of H0. Since the eigenbasis is complete, I can always do that with coefficients a n of t, but then we actually rewrote the coefficients and brought in the new coefficient c n of t by essentially taking out this e to the minus I by h cross epsilon n t term outside. Now the reason why we did that, as explained in the last lecture, was that simplified the differential equations involved. But there's another way to look at it, and perhaps that's also important to understand. Notice that if H0 were all of the Hamiltonian, that is H were equal to H0 and V of t were 0, then the states phi n would be stationary states for that particular system. What that means is, as time evolves, the time dependence that they would pick up is simply of the form e to the minus I by h cross epsilon n t. So what that means here is that this form that we have written down essentially takes into account the time evolution which the state would have had H0 been the entire Hamiltonian. In that case, the CNTs would have been just constants Cn, one for each phi n of course, but they would have been constants in time. Now, since we assume that our Hamiltonian is nearly H0, the perturbation V of t is in some sense small, we expect Cn of t, while not constants, to be slowly varying functions of time. So rather than the rapidly varying functions of time a and t that we had in the original expansion, in this expansion we have slowly varying functions of time, and because they are slowly varying, the time derivatives are small, which gives us this handle into perturbative calculations. Now we saw that if we substitute this expansion in the Schrodinger equation, you end up with this particular set of coupled differential equations, and where the v tilde mn essentially are the matrix elements v mn phi m vt phi n of the perturbing potential, but on top of that there is this extra piece exponential I by h cross epsilon m minus epsilon n t, which of course we shortened to exponential I omega m n t, where omega m n is epsilon m minus epsilon n by h cross. Of course, from high school physics we all know a physical significance, quote unquote, for this omega mn. If a transition were to occur between the states phi m and phi n, the photon that would be produced as a result would have frequency omega mn. So basically we end up with a coupled set of differential equations where v tilde mn's play an important role. And just to point out, apart from the time dependence which v mn might already have because of the fact that v, the perturbation, is time dependent, you have an additional time dependent phase factor. And as we said, we can rewrite this in the form of coupled integral equations. Again, this was explained in the last lecture, but this essentially is just a rewrite of the differential equations there. But to first order in perturbation theory, what we can do is we can get an approximation, the first order approximation for CMTs, these coefficients, simply by replacing all the CNT primes inside this integral by the initial value Cnt0. Just to remind you, why does this work? Because for each of the CNT primes, you have this same expression here, which essentially says that CNT prime is Cn T0 minus this whole term, again a similar term, and this term already has a V in it. So if you are ignoring anything higher order than one single V tilde, Cn T0 here will suffice. So this is the first order time dependent perturbation theory result, that you can calculate CMT but just by finding out this integral. And in particular, if you are starting from a given initial eigenstate, there is unperturbed eigenstate phi I, then these CNT zeros, well, they are mostly 0, only one of them, that is the ith one, is 1, and using that you end up with this simple expression, that the first order perturbation theoretic expression for CNT, provided you are starting from the energy eigenstate phi I, is the approximate sign of course tells you that this is first order only, delta Ni, that's of course the initial value, minus I by h cross times this integral. So at least the first order in perturbation theory, your major job in figuring out what will happen to the system involves calculating this integral and interpreting the result. Just to point out that V tilde Ni has this time dependence because of V Ni T prime, but it also has this additional to the I omega Ni T prime thrown in. So in the last lecture we had derived this equation, we had also seen some consequences of this for perturbations which last for a finite period of time, either by vanishing after a finite period of time or attaining a steady value after a finite period of time. In this we are going to take a look at what happens when the perturbation is sinusoidal, is switched on at some time t0 and then keeps on going sinusoidally forever. So this is the form of the perturbation we have chosen, and just to simplify our notation a bit, I have chosen t0 to be 0. So what is V of t? V of t is basically a sinusoidal variation if it is a minus I omega t, where f is some operator which is time independent, and this alone of course would not do because this alone would not be Hermitian. So to get a Hermitian operator out of this, what we do is we take its Hermitian adjoint as well, f dagger to the I omega t. So this is what V of t is for positive t, if e to the minus I omega t plus f dagger e to the power I omega t. Now what is this theta of t doing at the front? Is simply reminding you that the perturbation was not there for negative times. Remember, our t0 is 0, which means our initial condition has been set at t equal to 0. Prior to that there was no perturbation. Right at t equal to 0 you have switched on this perturbation. That's what the theta of t, the step function, which, let me remind you, is 1 for positive t and 0 for negative t. That's what this theta of t is doing here. So this is what our perturbation is, and it is very easy to calculate what the Ck for the kth state where k is not equal to I is going to be. Well, we are not just the reason why we are looking at k not equal to I is because if I know what the probabilities of going to other states are, then I can easily figure out what is the probability of staying in the initial state. So for k not equal to I, the delta ki term is 0, and just to remind you, this was the integral we were supposed to do. So delta ki, because we are talking of Ck, is 0. Then you have minus I by h cross the kith element of V t prime into the I omega ki t prime dt prime. That's the integral we need to do. Well, since V is this, Vki will be Fki e to the minus I omega t. Remember, we are doing it from, the integral is going to be from t0 to t, that means in this case from 0 to t, so all positive t, so theta t is going to be 1, so we don't have to worry about the theta t factor. This is going to be Fki, this is going to be F dagger Ki, and F dagger Ki, let me remind you, is Fik's conjugate. So if you just wrote down the integral that was there in the last slide, you are going to get minus I by h cross t0 to t, of course 0 to t in this case, Fki coming from here e to the I omega ki t prime into e to the minus I omega t prime. So, okay, there's a typo here, the bracket should have ended here, the dt prime should have been multiplying the whole thing. But this is fki e to the I omega ki minus omega t prime plus f star ik. Just to remind you, this is f daggers kith element, which is the conjugate of ikth element of f. E to the I omega ki t prime as always, that's there in both factors, into e to the I omega t prime. So this is what you have. And this integral is trivial to do. Why? Because fki and f star ik are maybe very complicated matrix elements of some operator, but they are time independent, so they can just be taken out of the integral. And then this integral is absolutely trivial to work out. Now this, of course, you might object that the integral works fine only if omega ki is not equal to omega, or omega is not equal to minus omega ki, because then there would be a divergence or division by 0. But as we will see, that those cases can be easily covered as limiting cases. So we will just go with this expression. And just to simplify the analysis a bit, what I am going to do is take out e to the I omega ki minus omega t by 2 from the numerator here, which leaves you with twice I sine omega ki minus omega by 2 t. So I have just taken half of this phase, exponential of half of this phase out, which leaves you with essentially to the I theta minus e to the minus I theta in the numerator, and that gives rise to sine, twice I sine theta. The I goes outside here, and the 2 I have just put in the denominator. And I have done exactly the same thing with the other term as well. Now this factor, or rather its square, is going to play an important role in what is coming. So what I decided was define a function, just to make the notation simpler. I have defined the square of this as a function of dt comma omega ki minus omega. So dt comma omega ki minus omega, square root of that, because the square of this is what d is defined to be. Here of course you have exactly the same factor, square root of dt, but omega ki plus omega. And from this whole bracket I have taken the e to the I by 2 omega ki t out, and so on, and you are just left with these factors here. The reason why I am taking the overall phase out is simple. The overall phase, of course, is going to vanish or become 1 when you take the mod square to get the probability. So that's why I have collected the I and e to the I by 2 omega ki t in one place. So to get the probability, of course, you need to take the modular square of this, and because you are taking the modular square of this, you are also going to square these quantities. That is precisely why we define the square of this already as what my d is. But before we proceed any further, let us take a brief look at the function d of t comma alpha, some argument. What I have done here is I have sketched the graph of d of 1 comma alpha. This should be very familiar to all of you. This is what dt of alpha is. That's the function that we talked about. The function itself should be very familiar, because this is what you have seen in the intensity pattern, say for a single slit diffraction. The point I would like to make here is the height of this function as alpha goes to 0. I plotted this as a function of alpha for a fixed value of t. As alpha goes to 0, the limiting value of this function simply is t square, so that's the height. So larger the t, the bigger the height. And as far as this function's width is concerned, you can estimate the width by talking about the distance between the two zeros on two sides. After the first minima here and the first minima on this side, the function becomes pretty small, so most of it is concentrated within the two closest minima, and the width of this, as you can easily see, is given by 2 pi by t on one side and 2 pi by t on the other side. Remember, sign vanishes when its argument is pi, so alpha times t by 2 equals pi means alpha is 2 pi by t, and this is 2 pi by t here, minus 2 pi by t here. So the width of this dt alpha function, essentially the region where dt alpha can be taken to be non-zero, is 4 pi by t, which decreases with larger and larger t. So as t becomes larger and larger, the function becomes narrower and taller. This should remind you of the delta function, and as we will exploit in the next lecture, that fact that for very large t this sort of looks like a delta function is going to be very, very important. But for the time being, let's just keep this in mind, that this typically, at least for large values of t, is a rather narrow function centered at alpha equal to 0. And that is going to be important in analyzing the results. So this is the result that we had. The coefficient for the kth state, where k is not the initial state, is simply given by this pure phase factor by h cross outside times this combination, and I have written the sinusoidal functions on these two sides in terms of the function d. And the arguments, of course, are omega ki minus omega for the first one and omega ki plus omega for the second one. Let me remind you that these two factors will peak when omega is equal to omega ki and omega is equal to minus omega ki respectively, and when t is large, is going to be a very sharply peaked function, tall but narrow. Now that this is ck, I can easily calculate the probability of translation by taking the mod square of this, which essentially means you have to multiply the function by its conjugate, and the calculation is straightforward. This of course goes away, you get 1 by h cross square, and alpha plus beta's mod square is basically alpha mod square plus beta mod square plus alpha beta star plus alpha star beta, or the last two terms can of course be combined to be written as twice real part of alpha beta star. So mod square of this term becomes 1 fki mod square dt omega ki minus omega, you are squaring this, plus fik mod square dt omega ki plus omega. But we warn you that these two terms are not necessarily equal, because we have not taken f, our operator which defined v of t, as a Hermitian operator. That is why we needed to use both f and f dagger to get the final form, and twice the real part of this thing times this conjugate of this thing. Of course, when I take this thing and times the conjugate of this thing, you get it is minus I omega t, fki, fik, the double conjugate makes the conjugation go away, times the square root of this. That is the probability of transition to a discrete state phi k. So today what we are going to talk about is this. Under a sinusoidal perturbation, what is the probability that you can go from an initial state phi I to another state phi k, where the state phi k is considered to be part of the discrete spectrum. So this is a transition from a discrete state to another discrete state, and that is the final expression for that. And now let us look at special cases. Well, as we said a while ago, this function is very sharply peaked near alpha equals 0. So what happens when either omega equals omega ki or omega equals minus omega ki? I'm just going to talk about the case when omega equals omega ki. The other case is similar. So that is what we call resonance. Physically, it means that the frequency at which the perturbation is being applied that matches the energy gap epsilon k minus epsilon I by h cross between the two states that we are talking about. Now what happens if that is the case? Then of course alpha, the argument, in this case omega ki minus omega, becomes 0, and that means this function becomes t square. The probability of transition from I to k in such a case simply is given by this term. I can safely ignore the other two terms simply because when this is large, when omega is equal to omega ki, the argument alpha for this one is very large, which means d is very small, this d. So this is a large term, this is much smaller compared to that, So is this, because it's multiplied by a small term. So basically you end up with this as your result, and you end up with fki mod square by h cross square into t square. That's because that's what dt is when the other argument is 0. Now as you can easily see, this probability keeps on growing with time, which means that this simply cannot be a correct form for the probability over long times. After all, the probability of a transition has to stay bounded. It cannot go beyond 1. So what this means is this expression will break down, and well, in retrospect it really means first order time dependent perturbation theory will break down unless t is actually smaller than this limiting time, h cross by f mod of fki. Of course, if the perturbation is small, fki is supposed to be small, then h cross by mod fki should be a rather large number. So this approximation, or this first order approximation to the probability, will be valid at least for some rather reasonable amount of time. But you have to realize that within the final result itself, perturbation theory essentially has signed its own death warrant. It has told you that you cannot use it beyond a particular time, at least in resonance. What happens when you are away from resonance? Well, there are two cases that we can talk about. When you are away from resonance, remember you are far away from both omega equals omega ki and omega equals minus omega ki. One case when you are far away from both is when you are right in the middle, omega equal to 0. And omega equal to 0 essentially means that there is no time dependence in your perturbation, or rather the only time dependence in your perturbation v of t comes from the theta d factor. This is a perturbation which was 0 for all negative time and has suddenly been switched on to the value f plus f dagger at positive times. Now for that, when omega is 0, it's easy to see that all these d's have the same value, right? This d is d of t comma omega ki, this is also the same. The square root of the product is also d of t comma omega ki, so you can take everything out, and it's perhaps even better to do it at the level of CKT directly for the calculation and then take the mod square. It's pretty easy to figure out that this is what your final answer is going to be. After all, when omega is 0, this is 1, this is 1. You essentially have fki plus f star ik into square root of dt omega ki, and when you take the mod square of that, the h cross square was already there, and all these other factors 4 by omega ki square, all of them come from dt alpha. That's it. So this is the probability. As you can see that in this case the probability actually sinusoidally oscillates between going from between 0 and a maximum value. And also let me point out that what is sitting in the denominator here is the energy difference between the two states, and if your perturbation is going to be a valid perturbation, or at least going to be something you should be able to treat like a perturbation, small perturbation, then this ratio fki plus f star ik mod square, which essentially is the matrix element of v mod square divided by the energy difference h cross square omega ki square, should really be small. So in this case at least there's no worry that you are going to end up with the probability which increases without any bound. After all, sine square is bounded, and because of the fact that this factor is expected to be small, you don't really envisage any problems with using perturbation theory here. At least first order perturbation theory works fine. The other extreme case could be when omega is very far away, either very large positive or very large negative. I'm just going to talk about the very large positive case here. The large negative case is essentially the same. And for that, what you can say is dt omega ki minus omega. All of these, when omega is very much larger than omega ki, then you can simply ignore the omega ki here in these arguments. Remember, dt alpha is an even function of alpha, which what that means is omega minus omega ki is equally good, or if you ignore omega ki, this is going to be dt comma omega. So will this, And if you use that, then easily end up with this result. Well, you don't directly end up with this result. You actually end up with terms like this, this, and this with dt's thrown out. But now remember that dt essentially for large values of t is a very rapidly oscillating function. Now that alpha, which here is the omega, is very large, the sine has a very large argument which changes rapidly with t, so sine will keep on going up and down very rapidly. Of course, what that means is that what you can do is that for a fixed value of omega, some perturbation frequency which is high enough, what you will see is very rapid oscillations in time in the probability, and for all practical purposes you can just use the average. The average of sine square, as you know, is half, and the average of the cos omega t sine omega t that you are going to get from this e to the minus I omega t here, that's going to be 0. So essentially end up with contributions from this with d replaced essentially by sine square being replaced by half. Of course, sine square is half, but you have a 4 by alpha square extra factor, so that's 2 by alpha square from, or 2 by omega square in this case. So 2 by omega square for the first term, 2 by omega square for the second term, and you're dividing by h cross square. So this result is obtained by first of all ignoring the omega ki's with respect to omega because they are too big. Then of course would have given you all three terms, but then because you have very rapid oscillations now that omega is large, what you can do is essentially talk about the average probability because the thing is oscillating too rapidly, and from the average only this one and this one is going to give, these terms are going to give contributions. This e to the minus I omega t is going to average out to 0. So this is what your expression for probability from I to k transition is. Now all of this is fine. These were things which you did. Again, this result is expected to be not too big. Why? Because the numerator is supposed to be small compared to h cross square omega square. Remember, omega is already much larger than omega ik or omega ki, and h cross square omega ki square, that's the energy difference squared. So that's what it means when you say the perturbation is small. Its matrix element is small compared to the energy difference. Okay. Now let us go on and talk about a case where we are going to talk, we do have a periodic perturbation, but we are going to treat that not using perturbation theory but exactly, and we will see that that case validates the approximations that we are, or the perturbation theoretic approximation results that we have found so far. Now this is a case where you are going to discuss a sinusoidal perturbation again, but in a two-level system. So we have a two-level system where the energies of the two levels is separated by E0. So by choosing the 0 of energy appropriately, the H0, which is the Hamiltonian for the unperturbed system, essentially has two diagonal elements. Half E0, that's the upper state which we denote by plus, the ket plus has energy half E0, and the lower state, the ket minus, has energy minus half E0. So that's simply shifting the energy, so 0, so that the average of the two energies is what we call, what we define to be the 0. So that's my initial Hamiltonian. This obviously has two eigenkets, plus and minus, namely 1 0 and 0 1 as column vectors, with energy eigenvalues half E0 and minus half E0 respectively. On top of this, we have applied a perturbation V of t. Ignore the double equals, this of course should have been a single equal, which is purely off diagonal. Basically our f operator that we talked about is the operator 0 f 0 0. F dagger of course is 0 0 f star 0. So this is what my V of t is. It's a Hermitian operator made out of f and f star, where f and f star are constants. So what is my h? H is simply the sum of these two, and we change our notation a bit. Instead of E0 we write H cross omega 0. E0, remember, is the energy gap between the two states, and that we write as in terms of the frequency omega 0, and F we write as half H cross omega 1. To do that, you can take an H cross by 2 factor out, and this is what your matrix looks like. Omega 0 minus omega 0 comes from here and here, and omega 1 e to the minus I omega t is simply F e to the minus I omega t, except for the half H cross which I have taken outside. Now, if you look at this matrix properly, this matrix after all is a Hermitian 2 by 2 matrix, traceless Hermitian 2 by 2 matrix, and all traceless Hermitian 2 by 2 matrices can be written down in terms of the sigma matrices, sigma 1, sigma 2 and sigma 3. And in this case it's very easy to figure out what the expansion is. We have omega 0 times sigma z, that's where the 1, 0, 0, minus 1 is coming in. Omega 1 has a cos omega t here and a cos omega t here, so omega 1 cos omega t is multiplied by 0, 1, 1, 0, which is of course sigma x. And omega 1 sin omega t has a minus I factor here, plus I factor here, so that's multiplied by the matrix 0 minus I 0, that's your sigma y. So this is what the Hamiltonian is. So it's basically H cross by 2 sigma vector, which is of course matrix valued vector with components sigma x, sigma y, sigma z, dotted with another vector with coefficients omega 1 cos omega t, omega 1 sin omega t and omega 0. So this is essentially the problem of a spin half particle in a rotating magnetic field. The spin half particle is assumed to have a magnetic moment of minus g mu, and if you put it in a rotating magnetic field which is given by a fixed component in the z direction and a rotating component in the xy direction. So it's a vector which is going round and round the z axis, with b perpendicular given by this b1 cos omega t and b1 sin omega t factor. Then h cos omega 0, this coefficient, and h cos omega 1 simply can be related to the b0 and b1. So this is straightforward. If you put a electron or any other spin half particle with a charge, of course, with a magnetic moment in a uniformly rotating magnetic field, you are going to end up with this Hamiltonian. So while this Hamiltonian describes sinusoidal perturbation applied to any two-level system, we have a direct physical example of that, which is simply a spin half particle in a rotating magnetic field. And that example, of course, is very, very important technologically. Things like NMR, nuclear magnetic resonance, ESR, electron spin resonance, all of these basically start with considerations of this, a magnetic moment in a rotating magnetic field. Now this is a problem which I claim is exactly solvable. So how do you exactly solve it? Well, let's set up some background first. This is something we had described earlier in a different context, but let's talk about this again. Remember, what we want to do is solve the time dependent Schrodinger equation. I cross del psi del t is h t psi t. So we want to find out psi of t. But what we do is, we try to simplify the problem by finding out psi r t. This is really a change of picture, like when you change from Schrodinger to Heisenberg or Schrodinger to interaction picture. Just a reminder, changing over from Schrodinger to Heisenberg picture essentially makes the time evolution problem trivial as far as kets are concerned, because then the kets no longer time evolve. Well, we are not going to do something as drastic as that, but we are going to change to another ket psi r t by putting in a time dependent operator r of t acting on psi t, and try to see what kind of Schrodinger equation psi r t obeys. And that's pretty easy to figure out. I just try to calculate I h cross del del t of psi r t. This of course is going to be I h cross times RT times derivative of this plus dr dt times this. Simple standard rule that is applied for products all over in calculus. And now you realize that IH cross del psi del t, this thing here is nothing but H acting on psi. So if you put that in, this first term becomes RT HT psi t. The second term of course is IH cross dr dt psi t. Now since I want an equation in terms of psi r, a Schrodinger equation so to speak for psi r, the fact that there is a psi t on the right hand side is a problem. I want to replace this with psi r t, and so all we do is write psi t as R inverse psi r t. I perhaps forgot to mention that before, but we are assuming R of t to be invertible. Actually we are assuming it to be unitary, so invertibility comes with that anyway. So once you throw that in, you get this whole thing in the bracket in front of psi r t. So it's IH cross del del t of psi r t is some operator acting on psi r t, and that operator is of course what you call the effective Hamiltonian for this particular picture. So the HR, the R picture Hamiltonian, is given by RT HT R inverse t plus IH cross dr dt R inverse t. So if we often can cleverly figure out R of t so that HR becomes either small or simple, then my life becomes easier as far as solving the Schrodinger equation is concerned.
So now that we have this general setup ready, how do we use this for the specific Hamiltonian at hand? Well, just to remind you, this is the Hamiltonian for which we want to find the time evolution, and as we talked about a while ago, the physical picture here is that of a spin half particle with a magnetic moment in a rotating magnetic field. So it seems natural to think that if we were to rotate the coordinate system at the same rate as the magnetic field is rotating, then in the new coordinate system the magnetic field will look like a fixed vector. And the problem of a spin half particle in a fixed magnetic field is one which we know how to solve exactly. So given this background, it's natural to choose for R of t an operator which will cause rotations about the z-axis at a rate omega, namely this particular R of t. Now let us see whether actually choosing this R of t helps. Well, we need to calculate HR, the R picture Hamiltonian for this particular R of t, and for this we need this quantity IH cross dr dt R inverse. It's very easy to see that if you were to differentiate dr dt, you will get I omega by 2 sigma z down. R inverse of course will cancel whatever exponential is left, and in addition to that you have an IH cross in the front that will give you the minus half H cross omega sigma z. So that was straightforward. What about RH R inverse? To figure that out, it's better if we look at R sigma I R inverse for I equals 1 to 3 separately first. Well, RT sigma z R inverse t is obviously sigma z because RT, this particular R of t, commutes with sigma z. So it's going to move right across sigma z and cancel the R inverse t here. That was easy. What about sigma x? Well, to calculate RT sigma x R inverse t, we need to use the Becker-Hausdorff lemma that we had discussed before, and if we use it, it's pretty straightforward to do the calculation. We will end up with sigma x cos omega t minus sigma y sin omega t. Given the fact that R of t produces rotations about the z-axis, this result should be pretty obvious, at least easy to understand. And what about sigma y? Well, RT sigma y R inverse t is going to be the same rotation acting on sigma y, so sigma x sin omega t plus sigma y cos omega t. There's a typo here, this should be sigma y. Okay, now if we take all this and plug it back, first of all let's calculate RT H R inverse t. That means in this H, of course you're going to put RT on the left, R inverse t on the right, and because these H cos omega 0 are just numbers, RT, R inverse are going to act essentially on sigma z, sigma x, sigma y separately, and once we put all of that in and use the magic of trigonometry, that is cos square theta plus sin square theta equals 1 and stuff like that, this whole thing will simplify very much. I urge that you take pen and paper and work this out, and you will end up with RT HT R inverse T is simply h cross by 2 omega 0 sigma z. This term of course doesn't change under R inverse, but this term simplifies a lot and becomes just omega 1 sigma x. So something which is a constant, the time dependence has been cancelled as expected. Of course, this is not the full Hamiltonian HR. For the full Hamiltonian, you need an additional IH cross dr dt R inverse term, which is plus minus half h cross omega sigma z. So you end up with h cross by 2 omega 0 minus omega sigma z plus omega 1 sigma x. So as promised, once we have applied this R of t, we have gone into a new picture, and in this picture, the Hamiltonian HR of t, the effective Hamiltonian in this picture, describes the interaction of a spin half particle with a constant magnetic field. So, since this Hamiltonian is a constant, the time evolution problem for this psi rt is equal to urt0 psi 0, that is finding out the urt0, the operator which is going to carry out the time evolution, is trivial. Urt0 is going to be simply the exponential of minus I by h cross the operator hrt. So it's the operator hr which is being exponentiated here, of course. But the important thing is hr is time independent, so the simple formula works. So by substituting hr, this is what we have to exponentiate. Now the properties of the sigma matrices that we have studied earlier tells us how to do this very easily. In particular, it told us that if I had this thing, if we exponentiated minus I theta by 2, where theta is any real number, into sigma dot n hat, where n hat is a unit vector. Of course, sigma vector here is just a vector whose components are sigma x, sigma y, sigma z. Then the result is simply cosine theta by 2 I2 minus I sin theta by 2 sigma dot n hat. If you have forgotten how this result is derived, let me just remind you of one thing. You can easily show that sigma dot n hat whole square is the identity. That means, of course, any even power of sigma dot n hat is the identity, and any odd power is simply sigma dot n hat itself. You just use this result and use the definition of the exponential operator in the form of an infinite series, and you can immediately read off this final result. Now, in this expression, of course, we do have sigma vector dot n hat. Well, you have sigma vector dot a vector, that is sigma x, sigma y, sigma z is being dotted with omega 1, 0, because there is no sigma y, and omega 0 minus omega. So these are the three components, omega 1, 0, omega 0 minus omega, of the vector which is being dotted with sigma. Of course, that is not a unit vector, but that's easily remedied. You find out its norm, divide by that, and then you're done. So the norm of the vector is simple. It's just you just take this vector and find its norm. You can immediately write down the result. Where this capital omega is nothing but the norm of the vector omega 0 minus omega comma 0 comma omega 1 by 2, and this capital omega is the driving thing in this oscillation. As you can see, you have cosine capital omega t, sine capital omega t all over the place. So capital omega, which is half of square root of omega 0 minus omega whole square plus omega 1 square, is what normalizes this whole vector. And now, once we have this, urt0 is known, but we want to get back to psi of t. Psi of t, of course, is R inverse t psi rt. So that's R inverse t urt0. So this combination R inverse t urt0 is the actual Schrodinger picture time evolution operator, ust0 psi 0. We already have an expression for urt0 in terms of the sigma matrices. We already
defined R in terms of the sigma matrix, sigma Z in particular. So the multiplication of R inverse with UR is not that complicated a thing. It's slightly messy. If you carry it out in full, you will get UST0. However, all that we really want to figure out here is what is the probability that a system which was in the ground state or the lower energy state, the state minus to begin with, evolves into the state plus. And for that, thankfully, we don't even have to do this multiplication. Notice the transition probability that we want is simply this. The state minus, the lower state, is what you start from. You apply UST0 on that, which is the time evolution operator, which takes you from time 0 to time t. And that this UST0 minus gives you the state at time t. And if you want to find out the probability amplitude, that there is a plus state in the result, that the system has been excited to the upper state, you take the bra plus and hit UST0 minus with that. That gives you the probability amplitude. You take the modular square of that, you end up with our probability. So this is what we need to calculate. Now, as I said, US can be found out by applying R inverse first, and or rather R inverse second, because the one on the left actually gets applied later. But you need UST0. You need this form. UST0 is R inverse URT0. However, R inverse sitting here would have acted upon the plus eigenket, which is an eigenket of sigma z, hence an eigenket of R inverse as well. Remember, R inverse is made only out of sigma z. And it's easy to see that all that this will give you is a phase factor. So if you take the mod square, that phase factor will simply give you 1. So you can simply forget about the distinction between US and UR for this purpose. So you can directly work with URT0, find the plus minus matrix element of that, take the mod square of that. Now what is the plus minus matrix element of UR? For that, let us go back to the expression for UR that we had here. Notice that this term is diagonal. Of course, it's just the identity. Sigma z is also diagonal. So both of these two terms are free of a plus minus matrix element. The plus minus matrix element actually only comes from this. Omega 1 by 2 divided by omega times minus I sine capital omega t. So that is the thing whose mod square will give you PFI, the transition probability. So that's it. The transition probability from the initial state I to the final state F is given by omega 1 square by 4 capital omega square sine square omega t. So as I said, this capital omega is what is driving the oscillation. The frequency of the oscillation is given by capital omega and it's called the Rabi frequency, this capital omega. Now, as you can see, what this is telling me is that periodically the probability of occupancy of the higher level is going to go up and down. It's never going to reach 1 as long as omega 0 and omega are different, because as long as omega 0 and omega are different, capital omega is more than omega 1 by 2. So this is going to go from 0, the system entirely in the ground state, to a superposition state where there is a high probability of finding a particle in the excited state, the system in the excited state, and then it's going to come down again, and all this is going to happen periodically. These are what are called Rabi oscillations. Of course, you can rewrite the omega 1 in terms of the original matrix element capital F, and now this form also tells you one thing. For small times, omega t can be, sine of omega t can be replaced by omega t, and then this simply gives you the result that we had before. Although this result, PFIT, is an exact result, for small times it gives you PFIT is approximately f mod square by h cross square t square, which of course is a quadratic growth of the probability that we talked about earlier. Also notice that at large times, the further terms in this expansion would actually cut in, and hence this probability is not going to increase without bound.
Of course it can't, being a probability, but the exact formula does show you that for small times you do get the result which we obtained by first order perturbation theory, and for long times is going to take over from this t square growth, is going to end up being an oscillatory thing. And a special interest is the case when you have resonance, that is when omega 0 equals omega, that is the rate at which the system is rotating, the magnetic field is rotating, exactly matches the energy gap between the two levels. Then what happens is capital omega is exactly equal to omega 1 by 2, and now this is what you are going to get. PFIT is sine square, there is a typo here again, sorry, this is going to be sine square omega 1 by 2 into t. But capital omega, again, that's the Rabi frequency in this case, is now just omega 1 by 2, and you are going to get nice oscillations, and these oscillations are going to carry you all the way up to the excited state. So here what you will see is periodically you will find a time at which the system is entirely in the excited state. Then it will come down again to a superposition, and then finally to the ground state back, again a superposition and the excited state, and so on. So these are the kind of oscillations which are very, very important in technologically. They are especially important in the context of nuclear magnetic resonance and or electron spin resonance, where this theory plays an very important special role. Now, so far we have been talking about transitions to discrete levels. This last example was a very special case where you have just had two discrete levels, a system with only two levels. A slightly more complicated situation arises when the level that the system transits to is part of a continuum of levels. This continuum of levels requires slightly different ways of thinking about normalization of the states and so on. This is a very important special case, and we will devote the next lecture to that. Bye for now.